Welcome to the final lecture of week 12, where we're going to talk about GEEs for binary and count data. We're going to cover an example in depth with for binary data, binary longitudinal data using a GEE, and I'm just going to talk about how you would code that and apply it to count data as well. And there are a couple nice tutorials online for this. So there's a Journal of Statistical Software article on the GPAC library that goes into some depth about how you might use different correlation structures other than the ones that are pre-built into the package if you wanted to try different correlations. And then the second link here is to a nice online tutorial that does an analysis with binary data using a similar data set to the one that I'm working with in the example here and goes into more depth. That would be worth taking a look at. Oops. So a quick note on GEEs in R that I want you to be aware of that I'm not going to go into detail with here, but I'll mention in lab, is that both the GEE and GPAC libraries have a quirk that you should know about and is mentioned at the link provided. And if you don't take this into consideration, results can be wrong. So I'll talk about that a little bit more in lab next week. So I'm going to go through a binary data example with respiratory illness, and this data comes from a clinical study in which the effect of a treatment on patients with respiratory illness was examined. And so there are 111 subjects in the study with 4 measurements each, 1 at baseline and 3 follow-up periods. And each response variable is binary, indicating respiratory status being good or poor. There's also a variable for treatment, where A indicates active treatment and P is placebo, a subject identifier, ID, visit, which is the time variable indicating the visit number, center, which is 1 or 2 for treatment center, sex, M or F for male or female, age in years at baseline, and the respiratory status at baseline, which can also be good or poor. So below I'm going to load the data and create a unique subject identifier. I'll also look at some patterns of missingness and count the number of observations at each time point. In this case, the data is actually perfectly balanced again, which means that the sandwich estimator is happy. So first I'm going to load the library, and then the data respiratory is actually a data set stored within that GPAC library. And the first thing I'm doing is making a new ID column by combining the IDs for center and ID. And this is just because in this data set there actually is not a unique data identifier, so I'm making one. And I'm also going to factor the treatment variable so that placebo is the reference group and the active is not the reference group, and similarly I'm going to factor the sex variable so that female is the reference group. So here I'm checking the number of subjects in the data set, and you can see that there is 111, and I want to make a table to see the number of observations at each visit period. There's 111 at each visit period, so we can see that all subjects are measured at every visit. As always, the first thing that I want to do is some exploratory data analysis when I'm looking at a new data set. And I would always make more than one plot, but I'm just showing one plot here in the interest of time and space. It's really hard to show good binary data plots when it's hard to show binary data trajectories over time as a spaghetti plot. They just don't really work out. Sometimes you can make heat maps or lasagna plots. But even if you don't look at the trends over time, it's good to look at the other trends in your data. In this case, I just made a bar chart that shows you at each visit and within the active and placebo the proportion of outcomes that can be either a 0, which is good, or 1, which is bad. Good respiratory status, bad respiratory status. And the code for making this plot is to the left. But I would say that from looking at this plot, there aren't very obvious trends in differences between the treatment. It looks that, and especially in differences in the treatment over time. It looks like maybe at the last time point that there are more people who have a good, there's a higher proportion of good respiratory status in the active group than in the placebo, but that pattern is not super obvious. So again, we want to check the correlation in some way as between the repeated observations as well, because that will help us give a good guess at our working correlation structure. And what I've done in previous exploratory plots for the correlation is to subtract the mean and then look at the residuals, the correlation and the residuals. And here I'm just going to check the correlation in the data rather than the residuals, which can also be a reasonable thing to do. But one way, and the reason I'm doing that is it's just a little bit easier to do it this way that for binary data, whereas with continuous data, it was pretty easy to just subtract the mean and then look at the residuals. But if you wanted to do sort of more of a residuals look, one thing that you could do is fit a logistic regression at each time point, subtract the mean value there, and then examine the residuals that way. So first, this code is producing a correlation plot at each time point. First, I'm converting the data to wide format. I'm selecting only the observations, only the columns that have to do with the observation of the outcome at each time point. I'm calculating the correlation, and I'm making a matrix of a plot of the correlation at each time point. And what you see from this plot is that here the correlation between month 1 and month 2, between 2 and 3, between 3 and 4, between 2 and 4. And you can see that the correlations hover around 0.4 to 0.6, and they don't seem to be decreasing that much in time. In fact, the comparison with month 1 and month 3 is actually lower than the comparison with month 1 and month 4. And they seem to be like relatively the same at each time point. So this would be potentially a good candidate for exchangeable correlation structure. So we're interested in a GEE model for this data with treatment, age, and sex as predictors. And we also want to control for outcome value at baseline. And so I'm calling this a logistic GEE model because we have binary data, and logistic regression is the sort of analogous model for what we're doing here. So this is kind of like longitudinal logistic regression, where the correlation structure accounts for the repeated measurements in subjects. And you'll notice here that I have treatment, age, and sex as covariates, but I'm not including time. In other longitudinal models we've looked at so far, I've always included time, but I'm not including it here because I want to point out that you don't have to include it in your model just because your data is longitudinal, especially with GEE models where we're looking at the population average. We're really only including the main effects for things that we're interested in clinically or interested in modeling. And the correlation structure is accounting for the repeated measurements in time, so you don't necessarily have to include time as a covariate. So the syntax for actually running this model is similar to what we did for continuous data with added features like that we would add for logistic regression, where in the formula I specify the mean structure, the predictors that I want to use in my model. I need to feed it the ID, the data. And then this family statement, I'm saying the family is binomial, like we did for GLMs. And again, the independence correlation structure is printed here. So the summary will be quite similar to what we saw for continuous data, except now we have a different family, which is binomial. And you produce a table of estimates here. In this case, we have the status at baseline is a significant predictor. The treatment does end up being significant, but sex and age are not. So I also want to check this model for exchangeable correlation, where we have the same correlation between any 2 points in time. And the only difference when I'm modeling that is to then just change this core structure argument. And I'm going to combine all of those coefficients into a data set so we can compare across the different working correlation structures. And I'm also adding a QIC in here so that I can look at the QIC for both of those models as well. And just looking at the output of that table, what we can see is that, okay, comparing independent to exchangeable, the estimates are very similar for the intercept. They're exactly the same for age, at least up to 3 significant digits. They're the same for baseline, for sex, and for treatment. And the standard errors are basically exactly the same as well in this case, which means that our inference is going to be exactly the same across models. So what do we draw from that? Well, for one, the fact that they're very similar indicates that it probably won't matter too much which model we choose if we're only interested in interpreting the population level estimates, because we're going to get exactly the same results if we choose the independence or exchangeable model. But why are they so similar in this case? Well, this is really an ideal condition for the sandwich estimator, because not only do we have perfectly balanced data, but we have a lot of subjects. We have 111 subjects, and we only have 4 visits for each subject. So not that many visits. So we have N is much bigger than N. And so it's really the ideal conditions for the sandwich estimator. So we're getting very, very similar estimates for both of these models. However, we do have to pick one. And even though they're both, I think it would be reasonable to choose either here, we would go with exchangeable because it has a little bit of a lower AIC. And just from our exploratory analysis, it did seem that exchangeable would be an appropriate correlation structure for this data. So how do we actually interpret these parameters? Well, for this is going to give you the same interpretation as logistic regression, with the added consideration that these effects are at the population level. So what I mean is that the exponentiated coefficients are odds ratios. They're not log odds ratios. That's a typo there. So the exponentiated coefficients are odds ratios. The coefficients themselves are log odds ratios. So here I'm just printing out the table of coefficients for the model we chose with the exchangeable correlation structure. You can see them here, and that's just so we can interpret them a little bit more easily. And first I selected the beta 0, which is not written out correctly here, but so that should say negative 0.537. That's the log odds of poor respiratory status for females age 0 with good respiratory status at baseline who received placebo. And this isn't interpretable because we don't have anyone close to age 0 in our data set. The beta for baseline is 1.997, and this is the log odds ratio of poor respiratory status comparing those with poor respiratory status at baseline to those with good respiratory status at baseline, controlling for the other covariates. And the treatment covariate is interpreted much the same way, which as the log odds ratio of poor respiratory status comparing those who received active treatment to those who received placebo. Because this is similar to how we would interpret logistic regression, we can exponentiate the parameters to get an odds ratio. The exponentiated baseline coefficient is 7.36. Yeah, that's right. Okay. So going back, the exponentiated baseline coefficient is 7.36, and we would say that the odds of poor respiratory status for those with poor respiratory status at baseline are 7.36 times the odds for those with good respiratory status at baseline, controlling for other covariates. So basically, having a poor respiratory status at the beginning of the study is highly indicative of having it later on. And we can interpret the exponentiated coefficient for treatment similarly as the odds of poor respiratory status for those who receive active treatment being 3.6 times the odds of poor respiratory status for those who received placebo. And that table is just printed here on the next page. Notice that I gave you confidence intervals this time. And these are all walled confidence intervals. We're not, all of the stuff that applied to the continuous data with no likelihood ratio test is still true for binary data. So what about count data? I'm not going to walk through an example in as much detail, but I wanted to give a couple things you might need to do this analysis with count data. So consider an example for epileptic seizures. This data comes from a clinical trial of 59 epileptics, where seizures were recorded during a baseline period and then in 4 consecutive 2-week intervals as well. And this is actually a real data set that is in the GEE package, so if you want to play around with it, go for it. And you have each of the different outcome variables at each of the time points. You have the baseline number of seizures, you have a treatment variable, and you have age in years. So if we wanted to run a GEE model, it's basically Poisson regression for longitudinal data. The syntax is similar to doing Poisson regression using GLM. Once again, using the GPAC package, I'm going to define my seizure model, and I put my covariates of interest here, and then I'm specifying the Poisson distribution for the family instead. And in this case, I'm running it with an exchangeable model, a correlation structure. So that's how you would run that model for a Poisson outcome. And this is going to specify a log link. And because it's specifying a log link, that gives us what we need to know to interpret the Poisson GEE model parameters. It gives us the same interpretation as Poisson regression, where the coefficients are log rate ratios. So if you exponentiate them, then you get a rate ratio. And you would just interpret that the same way that you did for Poisson regression.